Hello and welcome to Classes with Atish. Today we'll start a new series on vectors. Vectors will be important from AP Physics courses point of view. Specifically in AP Physics 1, you have vectors in single dimension and two dimensions. But I will go into a little bit more details and also talk about vectors in three dimensions in the later half of this series. So that helps you with the AP Physics C courses. For today, we will do a very basic introduction to vectors and also introduce you to the concept of vector addition and subtraction. So with that, let's get started. First of all, what is a vector? Vector is any quantity that has both magnitude and direction. Okay, whereas scalar quantities only have magnitude. Few examples: mass is a scalar quantity. It has only a magnitude, say some kgs. It does not have a direction. But speed is a scalar quantity, but we have another cousin of speed, which is called velocity. Velocity is a vector quantity because it has both magnitude as well as direction, which way it is going. So when we are able to represent both magnitude and direction for a quantity, then it's a vector quantity. So scalars, we can say distance, speed, mass. For vectors, displacement, velocity, force. Okay, there are many such examples. Next, let's talk about vector representation. So vectors are represented by arrows. Okay, so the length of the arrow gives me the magnitude, or it is representative of the magnitude, and the arrow itself is the representation of the direction. Okay, this is called the head of the vector, and this is called the tail of a vector. Okay, then we have the algebraic representation of vector. So if A is a vector, we will write it with the arrow on top of A. So it means this is a vector quantity. If I write it like this is a scalar quantity. Okay, let's say this vector quantity, we say is its magnitude is 2 meters. This is not complete because we haven't yet told which direction it is. But if I say 2 meters due east, then this is complete. Okay, similarly, let's say velocity represented by this v with the arrow on top. We say it's 5 meter per second, but I do not say which direction it is, then it is not the correct representation. We'll always have to add the direction. Let's say either we say east, west, north, south, or we can say along x direction or along y direction. Some direction should be mentioned. Okay, then it's a proper representation of the vector quantity. Now, few other things. If I represent with two lines on the side of the vector quantity, this is called modulus of a vector quantity. This represents the magnitude only. Okay. Coming back to this tail and head, if I represent one vector like this, okay, and if I represent another vector which is a little longer than this, you remember I said the length of this arrow represents the magnitude. This means this vector, let's say this is vector A and this is vector B, both have the same direction because they are pointing towards the same direction, but magnitude of A is greater than magnitude of B. Okay. Now let's look at another example. Let's say I have one vector B like this, and same length, but another vector A. It's the same length, but its direction is different. Vector A's, we can write vector A's modulus is equal to vector B's modulus, but which means the magnitude of them are same, but we cannot write vector A is equal to vector B. This is incorrect because their directions are different. Okay? All right. Okay. Now let's talk about different ways how we can classify vectors. First is equal vectors. We already kind of talked about that. Two vectors are equal if both their magnitude and direction are same. Okay. Unequal vectors. Two vectors are unequal if either their magnitude or their direction or both are different. Okay? So if either magnitude or direction are different, then they're unequal. Parallel vectors and anti-parallel vectors. If both the vectors are pointing to towards the same direction, then they are parallel vectors. If both the vectors, one is pointing this way, the other is pointing in the opposite way, then they are anti-parallel vectors. In this case, the angle theta between the two vectors is 0. In this case, the angle theta between the two vectors is pi or 180 degree. Okay. Next is collinear vectors. So if two vectors are in the same direction or in the same line, then they are collinear vectors. So both parallel and anti-parallel vectors are actually collinear because they are in the same line. Okay? Collinear meaning both are in the same line. Okay, not direction, just line. Next is coplanar vectors. Okay. So for this one, you will have to imagine 3D a little bit. So let's say this is my x-axis. This is my y-axis. And this is my z-axis. Okay. If I have two vectors, one here and another here, both are in the x, y plane, which means let's just imagine this board is my xy plane and z-axis is perpendicular to this board. Any vector I am drawing on this plane are coplanar because they are in the xy plane. Similarly, we can have two vectors which are in the xz plane. So these two we can say are coplanar because they are in the xz plane. But think about something. If I have any two vectors, let's just imagine these are two vectors, and this is my xy plane and the axis coming out of this plane, which is perpendicular to this plane, is the z-axis. Let's say it does not need to lie on this plane to be coplanar. Any two vectors, If I join them with a plane, they are in the same plane. So two vectors are always coplanar. You have to imagine this. Even if I put it at any angle in any orientation, these two vectors, okay, let's say I put it like this, I will always have a plane which contains both these vectors, okay, in any orientation I put, right? So two vectors are always coplanar. So this concept of coplanar vectors really makes sense when we have three or more vectors. Now these two vectors, let's say vector 1 and vector 2 are coplanar, but they are not coplanar with vector 3 or vector 4. Okay? So understand that concept, okay? What are coplanar vectors? Hope I made myself clear. Then we have concurrent vectors. Concurrent vectors are vectors acting on the same point. Like vector A and vector B. By the way, this is another representation. Either you can write it as with an arrow, or you can also write it with just a dash. Both are vector representations, okay? So concurrent vectors are vectors that are acting on the same point. Then we have zero vectors. What are zero vectors? Zero vectors have magnitude 0. What about direction? Direction can be any arbitrary direction. Because magnitude is 0, this direction does not matter. Those are zero vectors. Okay? It is still a vector quantity. If I say a force is 0, it does not mean now force has become scalar quantity. It has 0 magnitude, but any arbitrary direction. It can be any place. Okay? These concepts will become clear on edge cases, like the force is just about to go to 0, like static friction or dynamic friction, those kind of conditions. We will use this. So remember this, what are zero vectors, okay? And the last one is unit vectors. Now this one is super important. This one is super important. Let me explain it in this side. What are unit vectors? Unit vectors have magnitude 1 unit. Okay, that's what it is, unit vectors. So these vectors are used to give direction. Okay, now when I multiply a scalar quantity, let's say n is a scalar quantity, with a unit vector, it gives me the total vector. So this unit vector is giving the direction of the vector, and the scalar quantity is giving the magnitude of the vector. Now why this is important? Let's look back in our coordinate system. A unit vector in the x direction, okay, it is represented by x with a caret on top. It's called x cap. Okay, so this gives me the x direction. Similarly, a unit vector in the y direction is y cap. So its magnitude is 1, but it is giving me the y direction. Similarly, a unit vector in the z direction is z cap. Its magnitude is 1, but it is giving me the z direction. So why is this super important? This is very exciting now. Let's say vector A has some x component, some y component, some z component. We'll talk about components much more in detail as we go in the course, but we can write this as x, which is the scalar quantity which determines the magnitude in the x direction, times x cap, plus y times y cap, plus z times z cap. So what are x, y, and z? These are magnitudes in the x direction, in the y direction, and z direction respectively. And x cap, y cap, and z cap are unit vectors in the x direction, y direction, and z direction respectively. These have special names as well. This is usually called I cap, j cap, and k cap. So I cap means unit vector in the x direction, j cap means unit vector in the y direction, and k cap means unit vector in the z direction. Okay, unit vectors are super important, and we'll discuss more about this, and we'll use this very frequently in all our physics lectures. So pay special attention to this. Okay, so what are unit vectors? Magnitude is 1, and it gives direction of vector. Okay, this next concept is very critical. Okay, it's called, let me write it here, it's called parallel shift of vectors. Okay, so what is parallel shift? If I have a vector like this, okay, if I have a vector like this, I can shift it parallelly anywhere and it does not change. It remains the same vector. So if I shift it parallelly like this, here, these two vectors are equal vectors. They have the same magnitude, they have the same direction. This is all same direction. This is, don't think of it, it's different direction. It is the same direction. Similarly, if you have another vector like this, if I shift it parallelly this way, or if I shift it this way, these are the same vectors like this. It's the same vector. That's called parallel shift of vectors. And this parallel shifting will be important when we do vector addition and vector subtraction. Okay, so again, to reiterate, this vector and this vector, if I shift parallelly, or we do a parallel shift on a vector, it is the same vector. It is not different. It does not change. It is the same vector. Next, let's talk about angle between vectors. Again, this concept is very, very, very important. So pay close attention. Let's say I have two vectors like this. I have two vectors like this. I have two vectors like this, and I have two vectors like this. Okay, this angle is given as 90 degree, this is given as 30 degree, this is given as 110 degree, this is given as 60 degree. What is the angle between these vectors? Is it 90, 30, 110, 60 or something else? There is a way how you find the angle between vectors. The angle between vectors is defined as when you connect two vectors tail to tail or head to head. After you have connected two vectors tail to tail or head to head, whatever the angle between those two vectors is defined as the angle between the vectors. Again, you remember what is tail of a vector, what is head of a vector. This is called the head of a vector and this is called the tail of a vector. Okay, let's look at this one now. Is it connected tail to tail? Yes, this is the tail of this vector, this is the tail of this vector. So yes, the angle between these two vectors is 90 degree. Now let's look at this one. Are these vectors connected tail to tail or head to head? No, this one's head is connected to this one's tail. So what can I do to fix this? What can I do to fix this? What I can do is parallel shift. So let's say I keep this first vector like this, same orientation, but now this vector I shift it parallelly down and I shift it here. Can I do that? Absolutely, we can do that. So this vector that I shifted was here, I shifted it down. I did a parallel shift. Now this vector and this vector are the same thing. We talked about that in parallel shift, right? And now what is the angle between these two? That is the angle between these vectors. Okay, how much will that be? So if I extend this, if this was 30, then this becomes 150 degrees. Because this will be a straight line, it's 180 minus 30, which is 150 degrees. So angle between these two vectors is not 30 degrees, it's 150 degrees. Connect tail to tail. Same thing you could have done with this one if you would have done a parallel shift and connected head to head and then find out this angle. That would be the angle between vectors. Okay, in this case, are they connected head to head or tail to tail? They are connected head to head. So 110 degrees is the angle between these two vectors. How about this one? Again, I see head is connected to tail. So this time, let's keep this vector as is. So this is the parallel shift I will do. We will keep, let's call this B vector and let's call this A vector. We will call the keep the B vector as is, and this A vector we can either do a parallel shift like this. Yeah, that's what we can do, right? So we can move the A vector like this. I do a parallel shift of the A vector like this. So if I now extend this line, this would have been 60 degree. So this angle is 120 degree. So the angle between these two vectors is 120 degree. Okay. So that is how we find angle between vectors. Now another thing about angle between vectors, let's say we have one vector like this and another vector connected tail to tail like this. Now obviously these two vectors, they make two angles. One is theta angle between them, the smaller angle. The other angle is this outward angle, which is 360 degree minus theta. Which angle should we take as angle between vectors? The rule is angle between vectors should be greater than equal to 0 but less than equal to 180 degree. So if theta was 60 degree, then 360 minus theta will be 300 degree. So this does not fall in this range. So we will have to take theta equals 60 degree as the angle between the vectors. Okay. Okay. Now let's take a simple case of addition between vectors. I will discuss addition and subtraction of vectors in much more detail in the next edition, but let's take this simple condition here. Let's say I moved from this point to this point. So I move from A to B, and then I move from B to C. Okay. Now after this journey is done, if someone asks me what is my net movement, there is a special term in physics for that. It's called displacement. Displacement is your difference between your final position and your initial position. Okay, how do I find it? My displacement in this case will be from A to C. I started at A, I ended at C. This is the addition of this vector and this vector. Okay, so the addition of vectors has a special name. It is called a resultant vector. Okay, so AC vector can be represented as this as well. AC with the arrow on top of it is the resultant vector. And how did we get the resultant vector? I added AB, which is one vector, and I added BC, which is the other vector. Okay, now this addition of vectors will have to deal with it carefully. This method of addition is called head to tail method. Okay, do not confuse that with the angle between vectors. When we determine angle between vectors, we find the angle when the vectors are connected tail to tail or head to head. But when we are doing addition of vectors in this head to tail method, so you will see that this is the head of vector AB and this is the tail of vector BC. So how we get the resultant is we connect the head of the first vector to the tail of the second vector, and to get the resultant vector we connect the tail of the first vector with the head of the first vector and determine that with an arrow. Okay, so the vectors that we're adding, we connect the head to the tail of the other, and the resultant vector that we are getting is tail of the first vector to head of the second vector. Okay, now important things here. Let's say we want to add this vector and we want to add this vector. How would we do that? Well, first thing is we'll have to do some parallel shift. Now once you get used to it, you will do it very quickly, but I will show you some steps so you do not make mistakes as a beginner. So I can move this parallelly here. Okay, my goal is to connect the head of this vector to the tail of this vector. So this vector, now I can move it parallelly here. Now I have connected the head to the tail, head of first vector to the tail of the second vector. Now to find the resultant vector, I connect the tail of the first vector to the head of the second vector. This is my resultant. So I am using the parallel shift concept to connect the head of the first vector to the tail of the second vector. Let's take another example. Let's say I have one vector like this and another vector like this. Okay, how can I add these two vectors? Let's move this vector down a little bit. Do a parallel shift. And let's move this vector side a little bit. Do another parallel shift. Now the head of first vector is connected to the tail of the second vector. Now to get the resultant vector, I will connect the tail of first vector to the head of second vector, and that becomes my resultant vector. This is my resultant vector. Okay. Now, if I had to connect multiple vectors, let's say we had this, then we had this, then we had this, then we had this. So there are 4 vectors now. All are connected head to tail, head to tail, head to tail. What is the resultant of vector A, vector B, vector C, and vector D addition? The resultant will be tail of the first vector joined with the head of the last vector. This is your resultant vector. Okay. All right. So I hope addition of vectors, the head to tail method, is clear to you. Now, all this is good, so you can measure and find out what is the magnitude of the vector. But if you do not have the capability to measure, then we'll have to use some mathematics, some trigonometry to find out the magnitude of the resultant vector. So for example, a simple case, let's say I have one vector like this and another vector perpendicular to this. This is 3, this is 4. So I know how will I get the resultant vector. I will connect the tail of the first vector to the head of the second vector. This is my resultant vector with the direction. So this is the direction, this is my magnitude. Now I can use Pythagoras theorem in this right angle triangle, and I know this will be 5. So the resultant vector is 5 in this direction. Okay. Now, if I had a situation where one of these vectors was, let's say 3 like this, but now this is no more a 90 degree. Let's say instead this is a 60 degree. 4. Of course, we can find out the resultant vector by connecting this to this. But now I have difficulty finding out the magnitude of this unless I know some trigonometry. So that is where we will go into parallelogram law of addition to find out a neat formula so we can find out the magnitude of this as well as the direction of this vector compared to either the first vector or the second vector. Okay. Okay. Last point before we close this chapter. Vector addition is commutative. What does that mean? If I find out vector A plus vector B, this will be same as vector B plus vector A. Okay. How to prove that very quickly, very easily? Let's say we have vector A and we have vector B. So in this head to tail method, I connect the tail of first vector to the head of the second vector, and this is my resultant vector. So this is where I am computing A, which is the first vector, plus B. Okay? Let's shift B vector parallelly like this. So it will come somewhere here like this. Okay. And similarly, let's shift A parallelly like this. It will come here like this. Now, if I compute B plus A, so B head to tail of A, and how do I get the resultant? Tail of the first vector, in this case it was tail of B, plus to the head of the second vector, which is A, so R. So you see both these results compute to R, which is same. So therefore vector addition is commutative. So in the next lecture, we will continue with addition of vectors using the parallelogram law of addition. Okay, so see you in the next one.